Exercise 1.1, question number 2. Find 6 rational numbers between 3 and 4. So to find 6 rational numbers between 3 and 4, we have to convert 3 and 4 into their equivalent rational numbers. So to convert 3 and 4 into their equivalent rational numbers, we have to multiply both the numerator and denominator of these numbers by 1 more than 6, which is by 7. So 3 can be written as 3 by 1. Now we have to multiply both the numerator and denominator by 1 more than 6 by 7. So 3 by 1 becomes 21 by 7. And same also for the number 4. We can write 4 as 4 by 1. We have to multiply numerator and denominator by 7, which becomes 28 by 7. Now we have to insert 6 numbers between 21 by 7 and 28 by 7. So the required 6 rational numbers are 6 rational numbers are 22 by 7, 23 by 7, 24 by 7, 25 by 7, 26 by 7, and 27 by 7. Question number 3. Find 5 rational numbers between 3 by 5 and 4 by 5. Same here also, we have to multiply the numerator and denominator of both the numbers by 1 more than 5, that is by 6. So therefore 3 by 5 can be written as 3 into 6, 5 into 6, which becomes 18 by 30. And the number 4 by 5 can be written as 4 into 6 by 5 into 6, which is 24 by 30. So the equivalent rational number of 3 by 5 is 18 by 30, and the equivalent rational number of 4 by 5 is 24 by 30. So therefore the required 5 rational numbers are 19 by 30, 20 by 30, 21 by 30, 22 by 30, and 23 by 30. Next, exercise 1.3, question number 3. Express the following in the form P by Q, where P and Q are integers and Q not equal to 0. Roman number 1, 0.6 bar. So here we are given a decimal expansion which is non-terminating repeating decimals, and we are to convert this decimal into a number which is in the form P by Q, where P and Q are integers and Q not equal to 0. For this, let us assume this number, which is 0.6 bar, is equal to x. Therefore solution, let x equal to 0.6666. Now what we are going to do is we will multiply both sides of this equation by 10. Why 10? Because here in this decimal expansion the repeating digit is 1, that is the number 6 is repeated again and again. If suppose in a decimal expansion, if the repeating digit is of 2 like this, then we are going to multiply both sides of that equation by 100 and so on. So for this type of equation, here we are going to multiply both sides of this equation by 10. So now after multiplying both sides of this equation by 10, we will get 10x on the left hand side and 6.6666 on the right hand side. Next implies 10x equal to 6.666 can be written as 6 plus 0.6666 dot dot dot, such that this number becomes our x. Therefore, this implies 10x equal to 6 plus x, because 0.6666 is equal to x. Then after this we will solve this equation. So 10x minus x, I will transpose this x to the left hand side, equal to 6. This implies 9x equal to 6, implies x equal to 6 by 9. After reducing, we will get 2 by 3. So the given number 0.6 bar is converted into a number 2 by 3 in the form, which is in the form p by q, where p and q are integers and q not equal to 0. Therefore, the required number is 0.6 bar is equal to 2 by 3. Next, exercise 1.3, question number 4. Express 0.99999 dot 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 in the form p by q. Are you surprised by your answer? With your teacher and classmate, discuss why the answer makes sense. Exercise 1.3, question number 4, solution. Let x equal to 0.99999 dot dot. Then here we are going to multiply both sides of this equation by 10. Here also the repeating digit is 1. So after multiplying by 10, we will get 10x on the left hand side and 9.99999 dot 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 on the right hand side. Implies 10x equal to, this number can be written as 9 plus 0.99999 dot dot dot. Implies 10x equal to 9 plus, here this particular number is equal to x, so we will replace this number by x. Now we will solve this equation. So 10x minus x equal to 9, implies x equal to 9x equal to 9, implies x equal to 9 by 9, 9 by 9. Therefore x equal to, implies x equal to 1. Here we get the number 1 as our answer for the given number 0.9999. So the second part of the question says, are you surprised by your answer? Here the answer is not surprising, because as you can see the given number 0.9999 is very much close to 1. So we are expecting this 1 as our answer. So you can write, since 0.9999 dot 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 is very close to 1, we are not surprised by our answer. Next, exercise 1.3, question number 5. What can the maximum number of digits be in the repeating block of digit in the decimal expansion of 1 by 17? Perform the division to check your answer. Number 5, solution. Let us first find the decimal expansion of 1 by 17 by actual division. You can do the actual division at your home. So after finding out the decimal expansion of 1 by 17, we get 0 0.50583352941176447 as the decimal bar as the decimal expansion of 1 by 17. So here the repeating block is 0588235294117647. So the repeating block has how many digits? Let us count. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. So the repeating block has 16 digits. Next, exercise 1.3, question number 6. Look at several examples of rational numbers in the form p by q, where q not equal to 0, where p and q are integers with no common factors other than 1 and having terminating decimal representations. Can you guess what property q must satisfy? To answer question number 6, let us take up 4 numbers: 2 by 5, 3 by 2, 7 by 8, and 7 by 10 as our example. So 2 by 5, after converting into decimal, we will get 0.4. 3 by 2, after converting into decimal, we will get 1 by 5, and 7 by 8 equal to 0.875, and 7 by 10, of course, is equal to 0.7. So here the question asks you to find the property which satisfy the condition of q. That is the denominator, the number denominator q. So we have to find the property which satisfies the property of q, that is denominator. So let us first consider the number 2 by 5. So we have taken the number 2 by 5, which is in the form of p by q and q not equal to 0. Likewise, the other numbers 3 by 2, 7 by 8, and 7 by 10 are numbers which are in the form p by q and q not equal to 0, and there is no common factor between the numerator and denominator other than 1. So after converting these numbers into their respective decimals, we get terminating decimals, which the question asks you to take up such numbers. So as you can see, the denominator of these numbers are either in the power of 2 or in the power of 5. There is the denominator 5 is in the power of 5 and denominator 2 is in the power of 2, and here also the denominator 8 after their prime factorization we will get the 8 as 2q, and the denominator 10 as 2 to the power 1 into 5 to the power 1. So observing all this, we can conclude that the denominator are in the form of to the power of 2, either 2 or 5 or both, either 2 or 5 or both. So the property which satisfy the condition of the denominator q is they are all in the power of 2 or 5 or both. So we can write all the denominators are in the power of either 2 or 5 or both. Next, exercise 1.3, question number 8. Find three different irrational numbers between the rational numbers 5 by 7 and 9 by 11. So here we are to find three irrational numbers between the two given rational numbers. So one must remember that there are infinite numbers of irrational numbers between any two given rational numbers. To find these three different irrational numbers, let us first convert the given rational number into their respective decimal expansion. So 5 by 7 after decimal expansion we will get as 0.714285 bar. That is, the repeated block is 714285, and 9 by 11 equal to 0.81 bar. Repeating block is 81. So we are going to insert three different irrational numbers between these two decimal expansion. So therefore the required three irrational numbers are 0.750750075000 and 0.760760007600 0.8008008000. You can write your own different irrational numbers. Next, exercise 1.3, question number 9. Classify the following numbers as rational or irrational numbers. So in question number 9, you are given some numbers and you are to identify the given numbers are rational or irrational. So in Roman number 1, root 23. Root 23 is an irrational number. It is an irrational number. And Roman number 2, root 225. Here we have to observe that the number 225 is a perfect square. So root 225 is equal to 15. So 15 is not an irrational number. So this root 225 will be a rational number. And next, Roman number 3, 0.3796. So here decimal expansion is terminating. So if the decimal expansion is a terminating 1, the number is a rational number. And moving on to next number, Roman number 4, 7.478478 ... Here you can observe that the number 4788 is repeated again and again. So this type of decimal expansion is non-terminating repeating decimal. So for a rational number, the decimal expansions are either terminating or non-terminating repeating decimal. So Roman number 4 will be a rational number. Next, Roman number 5. In Roman number 5, the decimal expansion is non-terminating, non-repeating decimal. So this will be an irrational number. So exercise 1.5, question number 2, Roman number 2. So in Roman number 2, 3 plus root 3 whole into 3 minus root 3. Here we are going to use one of the identity for real numbers, that is a plus root b whole into a minus root b equal to a square minus b. So using this identity, 3 plus root 3 whole into 3 minus root 3 equal to 3 square minus root 3 square equal to 9. 3 square is 9 minus root 3 square is 3, that is root 3 into root 3 equal to 3, which is equal to 6. So after simplification, the expression 3 plus root 3 whole into 3 minus root 3, we will get 6. Next, exercise 1.5, question number 2, Roman number 3, root 5 plus root 2 whole square. Here we are going to use one of the identity for real numbers, that is root a plus root b whole square equal to a plus twice root ab plus b. So in other words, we are going to use the identity a plus b whole square. So root 5 plus root 2 whole square equal to root 5 square plus twice root 5 root 2 plus root 2 whole square equal to 5 plus 2 root 5 into root 2 equal to root 5 into 2 plus root 2 square equal to 2 plus equal to, here we will add 5 with 2 and we will get 7. 5 plus 2, 7 plus 2 root 5 into 2 equal to root 10. So after simplification, we will get 7 plus 2 root 10 as our required answer. Next, exercise 1.5, question number 2, Roman number 4, root 5 minus root 2 whole into root 5 plus root 2. So solution, root 5 minus root 2 whole into root 5 plus root 2. This will become root 5 square minus root 2 square, that is a plus b whole into a minus b equal to a square minus b square. Now root 5 square is 5, that is root 5 into root 5 equal to 5 minus root 2 square is 2. Now 5 minus 2 is 3. So for Roman number 4, after simplification, we will get 3 as our required answer. Next, exercise 1.5, question number 5, rationalize the denominators of the following. Roman number 1, 1 by root 7. So here we are to rationalize the denominator of the number 1 by root 7. So solution, to rationalize this number, we have to multiply both the numerator and denominator of this number by the rationalizing factor of root 7. That is, we have to multiply by root 7. 1 root 7 into root 7 equal to root 7 by root 7 into root 7 is 7. So the denominator becomes a rational number, so the final answer will be root 7 by 7. Next, Roman number 2, 1 by root 7 minus root 6. So here also, to rationalize the denominator, we have to multiply both the numerator and denominator by root 7 plus root 6, which is the rationalizing factor of root 7 minus root 6. So therefore 1 by root 7 minus root 6 equal to 1 into root 7 plus root 6. Root 7 minus root 6 whole into root 7 plus root 6. This is equal to root 7 plus root 6 by, this will become a minus b, that is 7 minus 6, using one of the identity, equal to root 7 plus root 6. The denominator will become 1. 7 minus 6 is 1. So our required answer will be root 7 plus root 6. Next, exercise 1.5, question number 5, Roman number 3, 1 by root 5 plus root 2. So solution, 1 by root 5 plus root 2 equal to, here also we are to multiply both the numerators and denominators by the rationalizing factor of root 5 plus root 2. Therefore it will be 1 into root 5 minus root 2 equal to root 5 plus root 2 multiplied by root 5 minus root 2 equal to, numerator will become root 5 minus root 2, then denominator will be 5 root 5 square minus root 2 square, root 5 square minus root 2 square equal to root 5 minus root 2 by, this will become 5 root 5 square is 5 minus root 2 square is 2 equal to root 5 minus root 2 by 5 minus 2 is 3. So after rationalizing the denominator, we will get root 5 minus root 2 by 3 as our required solution to the question Roman number 3. Next, exercise 1.5, question number 5, Roman number 4, 1 by root 7 minus root 2. So solution, 1 by root 7 minus 2 equal to 1 into root 7 plus 2, which is the rationalizing factor of the given denominator. So root 7 minus 2 multiplied by root 7 plus 2 equal to root 7 plus 2 by, this will become root 7 square minus 2 square equal to root 7 plus 2 by root 7 square is 7 minus 2 square is 4. So root 7 plus 2 by 3. So after rationalizing the given number, we will get root 7 plus 2 by 3 as our required answer. Next, exercise 1.6, question number 1, find the value of Roman number 1, 64 to the power 1 by 2, Roman number 2, 32 to the power 1 by 5, Roman number 3, 125 to the power 1 by 3. Now let us try to solve each of these questions. So first, moving on to question number Roman number 1, 64 to the power 1 by 2. So solution, 64 to the power 1 by 2 equal to, first let us prime factorize the number 64. 64 2 times 32, 2 times 16, 2 times 8, 2 times 4, 2 times 2. So therefore 64 can be written as 2 into 2 into 2 into 2 into 2 into 2. That is 2 to the power 6. So 64 is equal to 2 to the power 6. So therefore 64 can be written as 2 to the power 6 to the power 1 by 2. Now next we will use one of the laws of exponent, that is a to the power b to the power q is equal to a to the power b q. So using this identity we will get 2 to the power 6 into 1 by 2. So this will become 2 to the power 3. 2 to the power 3 is 2 into 2 into 2, which is 8. So our required answer will be 8. Next, let us try to solve Roman number 2, that is 32 to the power 1 by 5. So Roman number 2, 32 to the power 1 by 5. Solution. Same as first, we will prime factorize the number 32, 2 times 16, 2 times 8, 2 times 4, 2 times 2. So 32 can be written as 2 into 2 into 2 into 1, 2, 3, 4, 5. 2 5 times. So 32 is equal to 2 to the power 5. So 2 to the power 5 to the power 1 by 5. So this will become 2 to the power 5 into 1 by 5. This will cancel out. This will become 2 to the power 1, which is 2. So the required answer to the expression 32 to the power 1 by 5 will be 2. Next, Roman number 3. Roman number 3, 125 to the power 1 by 3. 125 to the power 1 by 3. Solution. Prime factorize, let us prime factorize as 125. 5 times 25. 5 times 5. So 125 can be written as 5 to the power 3 to the power 1 by 3 equal to 5. 3 into 1 by 3 equal to 5 to the power 1, which is equal to 5. So the required answer is 5. Next, exercise 1.6, question number 2. Find the value of Roman number 1, 9 to the power 3 by 2. Roman number 2, 32 to the power 2 by 5. Roman number 3, 16 to the power 3 by 4. And Roman number 4, 125 to the power minus 1 by 3. So let us first solve Roman number 1. Roman number 1, 9 to the power 3 by 2. Solution. 9 to the power 3 by 2 equal to 9 can be written as 3 to the power 2. 3 square is 9, so 9, instead of 9 we write 3 to the power 2, then to the power 3 by 2, which is equal to 3 to the power 2 into 3 by 2. This 2 and 2 will cancel out, then we will get 3 to the power 3. 3 to the power 3 is equal to 3 square is 9, 9 into 3, 27. this is equal to 3 cube is 27. So the required answer is 27. Again, moving on to the question Roman number 2, 32 to the power 2 by 5. Solution: 32 to the power 2 by 5 equal to 32. After prime factorization, we can write 32 as 2 to the power 5 to the power 2 by 5 equal to 2, 5 into 2 to the 2 by 5. 5 and 5 will cancel, equal to 2 to the power 2, which is 4. 2 square is 4. So for Roman number 2, the required answer is 4. Next, let us try to solve the remaining Roman number 3 and 4. So Roman number 3, 16 to the power 3 by 4. Solution: 16 to the power 3 by 4 equal to, instead of 16 we can write to the power 4. That is 2 to the power 4 is equal to 16. This will become 3 by 4, which is equal to 2 to the power 4 into 3 by 4. 4 and 4. Then this will become 2 cube equal to 2 cube is equal to 8. So the required answer is 8. Next, Roman number 4. Roman number 4, 125 to the power minus 1 by 3. Solution: 125 to the power minus 1 by 3 equal to 125 of the prime factorization. We can write 125 as 5 to the power 3. So 5 to the power 3 to the power minus 1 by 3 equal to 5 to the power 3 into minus 1 by 3. 3 and 3 will cancel each other, equal to, this will become 5 to the power minus 1. Here we have to remember one of the laws of exponents, that is 1 by a to the power n equal to a to the power minus n. So 5 to the power minus 1 can be written as 1 to the power 1 by 5. This will become 1 by 5 according to this law of exponent. So the required answer to Roman number 4 is 1 by 5. Next exercise 1.6, question number 3. Simplify Roman number 1, 2 to the power 2 by 3 multiplied by 2 to the power 1 by 5. Roman number 2, 1 to the power 1 by 3 to the power 3 whole to the power 7. Then Roman number 3, 11 to the power 1 by 2 by 11 to the power 1 by 4. So let us first solve Roman number 1, that is 2 to the power 2 by 3 multiplied by 2 to the power 1 by 5 solution. So here we are going to use one of the laws of exponent, that is a to the power p multiplied by a to the power q equal to a to the power p plus q. So applying this law, 2 to the power 2 by 3 to the power 1 by 5 equal to 2 to the power 2 by 3 plus 1 by 5. Having these two fractions, we will get 2 to the power 2 by, taking the LCM, that is 5, LCM of 5 and 3, 15. This will, numerator will become 10 plus 3 equal to 2 to the power 13 by 15. So after simplification, we will get to the power 13 by 15 as our required solution to the question number Roman number 1. Next, Roman number 2. Roman number 2. One by solution equal to, here the number inside the bracket can be written as 3 to the power 1 by 3 to the power minus 3 to the power 7. This is equal to 3 to the power minus 3 into 7 equal to 3 to the power minus 21.